We're going to, brilliant, thank you. So we're going to kick off this event by saying, welcome everyone. This is several groups today, several use R groups from Scandinavia joining in. My name is Dmitro. I am in Skåne in Sweden, but we also welcome our friends in Norway, Oslo, and Copenhagen, and maybe some other locations. Feel free to drop in the chat if you're from exotic country. But other than that, we're very pleased to have yet another event that joins several countries together and unites us around R, using R, and sharing passion for analysis of the data. Today, we have a pleasure of welcoming Matthew Kay, assistant professor in computer science and communication Northwestern. He is working with uncertainty, visualization of uncertainty, and human-computer interaction. I've read a number of articles that are really state-of-the-art, pioneering research on visualization of uncertainty, and we're very pleased to have Matt today speaking to us. As I said, this is an event that was organized by several groups, Use R, in Skåne, Use R in Oslo and Copenhagen, but also this event is hosted by Bayes Lund. This is the initiative that goes back several years, and my co-hosts today, Ulrika and Rasmus and other participants have been organizing events related to Bayesian analysis and Bayesian statistics and all the toolkit that goes along with it. And so this event is also continuing that tradition. So we're going to have more events later this fall. We will talk about them at the end, but just wanted to bring this up, that this is also something that has history, basically, and many recordings are posted on the internet, and you can watch previous conferences, Bayes Lund, that we had here in Lund. I think that's as much as I want to say maybe at this time. If Ulrika or Rasmus want to say a few words. Other than that, I think we will be prepared to kick off the event.
I say let's kick off.
Brilliant. Matt, the floor is yours.
Okay. Thanks for that very kind introduction. Yeah, I'm excited to be talking about uncertainty visualization with tidybayes and Ggdist today. Also, as Dimitri said, I do research on uncertainty visualization. So I study how people interpret uncertainty visualizations, how people make decisions under uncertainty when presented with uncertainty visualizations. So I'm going to talk both sort of about ways of communicating uncertainty through visualization and also some of these tools that I've created to try to make it easier to do that, particularly from the output of Bayesian models. So I, many years ago, well, we all have relative definitions of many, 6 or 7 years ago when I was doing my PhD, I started building this tool, tidybayes, because I was fitting Bayesian models and finding it difficult to take the output of those models and munge them into an appropriate format to use them with Ggplot. And so I built tidybayes as a way of sort of bridging that gap. Eventually, it kind of grew into these two packages, tidybayes and Ggdist, where tidybayes is sort of focused on getting data into a tidy format, sort of long format data frames appropriate for use with Ggplot, and Ggdist has a bunch of geometries and other sorts of tools to try to make it easier to actually visualize uncertainty with Ggplot. And so I'm going to talk about those a little bit, actually a fair amount later on. I want to start, though, with this topic of strategies for effective uncertainty visualization. So based on my research and others' research, what do we know about uncertainty visualization? What do we know about some of the pitfalls in uncertainty visualization? What makes it hard? And why would we want to build tools to try to make it easier? And then sort of wind our way to some examples of constructing uncertainty visualizations with tidybayes and Ggdist. And I'm also going to talk a little bit, if we have time, do some demos, and some of those might also involve this Posterior package, which is a relatively new package that Paul Christian Berkner of BRMS and Jonah Gabry of RStan and RStan ARM and myself have been working on as another sort of piece in the toolkit for munging posteriors and sort of dealing with getting those into sort of a reasonable format for running diagnostics or building visualizations or what have you. The other thing I do want to say at this point, Dimitri just put it into the chat. Yeah, please ask questions. I think they will then be filtering questions to me. I am totally comfortable with being interrupted with interesting questions, and I'll also have points throughout the talk where if questions come up, I can talk about them. Or if there's something at the end, I'm going to try to do a chunk of demos. If there's something you want demoed, I'm happy to try to do that on the fly, and we'll see how effectively that goes. Okay, but I usually start my talks, and if you've seen like my StanCon talk or something, a small amount of this might be deja vu, and I apologize, but I'm going to be showing more content that isn't. But I usually start by talking about, with uncertainty visualization, sort of what happens when you ignore uncertainty, and what are some of the problems that can arise. These are probabilistic predictions of Trump's chance of winning the 2016 presidential election. So not the most recent one that he lost, but the one in 2016 that he won. So these are from 3 different poll aggregators, 538, New York Times, and Huffington Post, who gave him respectively a 28% chance or a 15% chance or a 2% chance of winning that election that he did ultimately win. And so these are based on models that are aggregating polls and often some other indicators like economic indicators, and then trying to make some prediction of the chance of Trump or Clinton in this case winning the 2016 US presidential election. The interesting thing I think about this is, even 4 or 5 years later, you still had people who were kind of thought that this prediction, say from 538, that he had about a third of a chance of winning, was a bad prediction. But of course, if you think about it in a sort of probabilistic sense, if you say there's a third of a chance of something happening, there's actually a quite reasonable chance that it will. If you wanted to judge the quality of the forecaster, you might instead ask something like, how well calibrated are they over a large number of predictions that they make? When they say something has a third of a chance of happening, does it happen a third of the time? 538 actually publishes their calibration information, and they're not too bad on their presidential forecasts. So I wouldn't say necessarily that this third of a chance is a bad prediction, but it might be a bad way of presenting that prediction. So this is an alternative way of presenting the same information. This is something called a risk communication theater. The idea here is, say in the 538 one, I have a seat map to a theater with 1,000 seats in it. I've given you a ticket to a random seat, and I've colored the seats black in proportion of Trump's chance of winning the election. I hope you might agree with me that it feels less surprising from this representation to learn that you maybe ended up in a black seat and Trump won the election than when I just told you there was a 28% chance of that happening. And so the point is that we're often very good at ignoring uncertainty, but this is especially true when we provide bad uncertainty representations. Risk communication theaters are an example of something called an icon array. It's used in medical risk communication to communicate things like different possible outcomes from alternative treatments to some condition, for example. And we call these frequency framing or discrete outcome visualizations of uncertainty. The idea of, rather than a sort of continuous encoding of there's a 28% chance, which, maybe I do as a bar chart, something like that. I show you this grid of 100 or 1,000 possible outcomes. And then maybe the idea is something like you can sort of imagine that you might be one of these people and sort of try to reason through what the implications of the different possible outcomes might be. So long ago, I worked on this this question, which is what's an icon array for a continuous distribution? So this is already a discrete distribution with just two possible outcomes. In this case, is successfully cured or not. If I have a continuous distribution, is there a way that I can capitalize on this similar sort of way that people reason about uncertainty and give you a representation that's maybe helpful for people? So I'll give you an example scenario. When I was doing my PhD in Seattle, there was a system, it's still there, it's called One Bus Away. It tracks where all the buses are in real time in Seattle and then tries to predict when they're going to show up at the bus stop. The Seattle buses are not always reliable. And the tracking itself is also not necessarily reliable. So GPS in urban areas can be inaccurate. Buses can hit traffic and so on. So the actual prediction of the arrival time has uncertainty associated with it. This representation is telling me, for example, the bus number 120 has a 6-minute delay. It's going to show up or predicted to show up 11 minutes from now. There is an uncertainty representation in this display. At the bottom, it says bus arrival estimates are based on the best available information, but actual times will vary. Well, I don't know how useful this is to me, right? Do I have time to get a coffee before my bus shows up? It says 11 minutes. It also says a 6-minute delay. Like maybe the bus driver will make up some time and get there 5 minutes from now. And if I walk across the street to get a coffee, I'll miss my bus. So right now the system is telling me something like this, right? I have a timeline from now off into infinity. Your bus is going to show up exactly 11 minutes from now, is what the system's telling me. What I probably want is something like this. So here's a probability distribution over time to arrive at the bus, just as a density plot. If you look closely, you'll notice that it is a little bit skewed, which makes sense for arrival time data. There's a reasonable chance it's going to show up somewhere in the like 8 to 15 minute range, but there is kind of a long tail. Maybe the bus gets stuck in traffic. Maybe something else crazy happens. When I was in Seattle, a fish truck turned over one day on the highway and basically stopped traffic in the entire city, which would be, way out here. So, these things happen. But I mean, this isn't really what I want either. Like what I really want is something like this, which is, if I show up at the bus stop 8 minutes from now, there's a 90% chance that the bus comes after me. And of course, if the bus comes after me, that's the same thing as me catching the bus. But I mean, this isn't really what I want either. So the problem is, depending on my circumstances, my risk tolerance is going to change, right? Like maybe I definitely want to catch this bus. I have a really important meeting. This goes up to like 99.999%, and I'm going to show up at the bus stop like 5 minutes from now. Or, maybe this is lunch with friends, or I know there's some alternative transit options that I have, and my risk tolerance is more like 75% here. So the point is that there isn't really one representation or one number that I can give to everyone to satisfy their risk preferences at this particular moment. And so I really want some way of communicating this distribution to people in a way that helps them reason about what they want to do. So you might say just show them the density plot, but now you kind of run into a different problem, which is area perception in humans is biased. So normally I do this interactively, but I don't want to like spend the time to go through the whole loop here. But take a second to think like how large you think in terms of area this smaller circle is as a proportion of the total area of these two circles. And my guess is most people, and I've run this demo a number of times, are going to say something like, oh, the smaller circle is about 80 or 85% the area of the outer circle. And the smaller circle is actually 75% of the area of the outer circle. And this is just due to systematic bias in area perception in humans. So as things become larger in terms of area, we don't perceive them as large as they are relative to smaller objects. And so as a result, you see the larger full area, which is the denominator in that ratio, as being too small. So you overestimate the ratio and you think it's more like 80 or 85% than 75%. And so the point that I'm trying to make here is essentially maybe a density plot isn't the best thing for this particular task. Like we know here probably people want to do this kind of one-sided interval estimation for figuring out the chance of their bus showing up and figuring out the chance that they're going to catch the bus. So maybe we want a representation that makes it easy for them to do that. Well, one way of doing that would be to show them the CDF instead, right? So here we're just taking the integral of the bottom. So if I read up at 10 minutes and then read over, this is telling me about 25% of the area of this under this curve is to the left of 10 minutes. So if I show up at 10 minutes, I have a 25% chance of missing the bus. I have a 75% chance of catching the bus. What I also said at the beginning of this little section, I wanted something that's going to be the analog to an icon array, a sort of discretized representation for a continuous distribution. So what I'm going to do instead is actually take, in this case, 20 equally spaced values in probability space and project them back into time, and then stack them up into a dot plot. And this makes something that I've called a quantile dot plot. And so the idea here is to try to bring in those notions of discrete representations or frequency framing of uncertainty to this continuous domain. And one of the interesting things, or one of the interesting properties of this, when you construct the chart in this way, is that interval estimation, which really is what we want here, right? I want to know what the chances that my bus comes before or after a certain time point is, becomes a counting task. So I can say something like, oh, if I show up at the bus stop 8 minutes from now, I miss 2 out of 20 of these hypothetical buses. I catch 18 out of 20 of them. So I have a 90% chance that I catch the bus. The other thing that's kind of cool here is, depending on the denominator that you choose and depending on where in the distribution you expect people to want to make these sorts of estimates, you don't even really have to count. So there's this thing that we can do called subvertizing, which is up to collections of size about 5 or 6. We can just sort of nearly instantaneously recognize like how many elements are in that collection, right? So you don't have to count that there's 5 elements here. You just know that there's 5 elements in this collection. And so here, if I choose a dot plot with a denominator of about 20, these, tail probabilities kind of in this region and this region are going to be pretty easy for me to find because I don't really have to spend time counting. I can just sort of quickly estimate, a point that will cut off 2 or 3 or 4 or 5 of these hypothetical buses. And so, I mean, I'm not going to get into it too much in this talk, but we've done some experiments on these sorts of representations, including these kind of incentivized decision-making experiments. And in this bus catching scenario, we find that it allows people to do better in terms of, say, expected payout on an incentivized experiment where we're showing people uncertainty representations and asking them to make decisions about like when to go catch a bus, and then penalizing them for being at the bus stop too long, and rewarding them for getting to where they want to go on time. And so the idea really here is to, I think the broader idea is to think about what does this say about how we should design uncertainty visualizations. And really, I think it's hard, right? You have a bunch of things that go into doing it well. You have the requirements of the task. So in this case, that you have really the thing that you care about is these kind of one-sided intervals in this particular decision-making scenario. You have things we know about visualization perception, like the fact that area perception is biased, and things that we know about uncertainty cognition, like maybe the value of frequency framing to helping people improve their decisions, and that we can use these things together to create more effective uncertainty visualizations. So one of the things that was kind of neat was a couple of years after that, so the 2016 election, where a lot of people were sort of upset for reasons also other than, obviously for reasons other than just the perceived quality of the predictions. One of the neat things was the 538 visualizations changed in the 2020 cycle. And one of the things that they started doing was this chart, which is essentially that sort of quantile dot plot style approach to communicating the uncertainty in their predictions. So here it's the predictive distribution from their model for the number of electoral votes, or actually I guess the margin in electoral votes. I've heard through the grapevine that they were influenced by the stuff that we had done around quantile dot plot. So this was kind of a neat thing to see kind of get out into the world. One of the other things that I did during the 2020 election was I took some of the data feeds from some of these poll aggregators and tried to think about other ways of presenting this information as well. So there's this idea that one of my colleagues, Jessica Hullman, works a lot on called hypothetical outcome plots. And the idea is to use animation to show uncertainty. And she's studied them in a couple of contexts. And it's motivated in a lot of the same ways by this sort of frequency framing thing I was talking about with quantile dot plots. The idea that, seeing individual outcomes. So rather than showing you the distribution, I like animate some outcomes from a distribution, allows you to experience that uncertainty and maybe makes it a bit more visceral. So during the 2020 election, I built this thing called Presidential Plinko, which I'm going to open up. Excuse me. And maybe zoom in a bit. And the idea here, if you've ever seen like a Galton board or a bean machine, or, in the US popular culture, you might think about Plinko, which was one of the games on The Price is Right that people would play. This is something where it has, I think, a more intuitive, I hate the word intuitive, but it's like, you're trying to get at a sort of mechanistic approach to communicating uncertainty, this thing that we already associate with a sort of random process. And so the idea that I had was basically to take forecast distributions from these forecasters and excuse me, something caught in my throat. Take these forecast distributions, back out a Plinko board that would generate essentially the same forecast distribution, or a distribution with the same mean and standard deviation. So basically, you can figure out if you have a bin size and you want to take like a binomial distribution and scale and shift it along this axis, you can figure out what the number of rows you need is to generate a distribution that looks like this. Pretty straightforward. And so then really actually the height of this board is then proportional to the spread at the bottom in a way that I think is kind of intuitive. If you have a more precise prediction, the board becomes smaller. If you were to drop something at the median of the predictive distribution, it's not going to move very far from that median. The height of the board goes up, it will move much further from the median. So then I built this website to essentially demonstrate, here's the predictive distributions from two different forecasters, essentially the night before the election. And you can see that, the bulk of both distributions are to the right of this line, which is when Biden wins the election. The other thing that you can do with this is you can just drop one ball at a time if you want, and sit here and kind of experience the uncertainty in the election outcome according to these forecasters. And if I click this long enough, eventually I'll probably get a Trump. There you go. So it eventually got to the point where I got a Trump win. But this was for the 2020 election again, where he lost. And then at the end, I had this sort of this is the final electoral count against the predictive distribution from The Economist. I didn't actually even end up updating this at the end because by this point it was clear that it was going to end up in this bin. So this is still where it ended up, even though these are still listed as uncalled. And so here it's sort of, the question is like, well, if you look at this and where you drop the ball and the height of the board, like, is it that surprising where the final vote count ended up? I would argue, probably not. So again, the idea is trying to think through like how you might create an uncertainty representation, in this case for, maybe a lay audience that allows people to experience the uncertainty and maybe reason about it in a bit more of an intuitive way. This, let's see, also has an R package. So I built all of these things in R. It's an experimental package. So, happy for people to try to use it and tell me if it's usable at all, if you want to try to build these things. But it essentially helps you build these animated Plinko boards for somewhat arbitrary distributions. I mean, as long as they're symmetrical, you can probably build something reasonable as an approximation to it. Cool. So I'm going to run through some more examples in a second. I guess this is a good point to pause and see if there are any questions about anything I've talked about.
Not at this moment.
Not at this moment?
Not at this moment, but we would like to encourage everyone to think of questions and ask them so that in pauses like this, we could ask good questions. Thank you, Sophie.
Cool. Okay, so some more examples of uncertainty visualization types and some pitfalls you can run into when you're trying to build uncertainty visualizations. So this is the classic hurricane error cone. This is, in this case, I believe a 95% predictive cone for where the center of the hurricane will be at, a couple of time points after wherever it is now. One of the interesting things about hurricane error cones, they've been studied in the uncertainty visualization literature fairly extensively, is you'll get these things called deterministic construal errors in interpretation of them. And a deterministic construal error is essentially when someone takes a uncertainty visualization or a representation of uncertainty and misinterprets some aspect of it as being a more deterministic part of the prediction than being related to the uncertainty in the prediction. So here, you might get about a third of people making the, I think, quite reasonable misinterpretation of this chart that it's showing you the predicted size of the hurricane rather than the uncertainty and where the center of the hurricane will be. And this is a reasonable misinterpretation because typically when we see maps, size represents geographic size. So to look at this and have size not represent that is in some ways a little bit weird. And so it's not an unreasonable misinterpretation. But there are ways that you can kind of try to mitigate against this. So this is something called the spaghetti plot. Here, it's just if you have a distribution for like a predictive distribution for the paths that the hurricane might take, you instead overlay a whole bunch of draws from that distribution. And so now this will mitigate that misinterpretation because we aren't really encoding size anymore. The other thing that's nice about this is that, you start to see more of the sort of relationship, more of what the distribution is really telling you about the shape of this curve. One of the problems also with this kind of representation with uncertainty bands, especially with regression lines and things like that, is often the median curve is not even a curve that's possible in the distribution, right? And so here, that may not really be the case, but this often comes up in things like, Gaussian process models and things like that. So you can apply the same sort of thing to fit line uncertainty in order to try to communicate something about, the uncertainty in this particular regression fit, for example. I think one of the really interesting use cases, or one of the reasons why spaghetti plots are really helpful, is when you have correlation in the distribution, right? So here's a data set that I just generated for the purposes of this example, with a bunch of time steps. In this case, there's high correlation between time steps on the left, and I've just decorrelated each subsequent time step on the right. But the marginal distributions here are exactly the same. If I put intervals over this, in fact, you won't even be able to tell the difference between these two charts at all. And this is really problematic. I mean, this comes up all the time. You'll even see people, the even simpler example of this is just like, look at two marginal distributions for two estimates you care about, right? If you want to know the uncertainty and the difference between those two things, you cannot determine it from just looking at those two marginal distributions, because they could be correlated, they could be independent, and you don't know. What you have to do is look at the distribution of the difference, right? So this is a really important thing to think about. It's like, what is the task you actually want to do with this visualization? Does this correlation matter? And if so, you know, a uncertainty band representation might not help. On the other hand, if it doesn't, like, you know, if you just care about like conditional on X value, what is the distribution, then it doesn't matter, and the uncertainty band might be fine. I'm going to run through one more fun example that I think is kind of interesting and a little bit weird. So communicating uncertainty in maps is a really very difficult problem. So here, each of these is a county in the US. It's trying to show the poverty rate and some aspect of the uncertainty, in this case, margin of error, simultaneously, right? And I think it's really hard to look at a representation like this and integrate these two pieces of information in order to then make a decision, right? Like, if the thing that you actually care about was, you know, like the likelihood of poverty rate being within a particular range or something, it's really hard to imagine like how I'm going to integrate the amount of yellow and the amount of blue in order to try to answer a question like that. So I'm not a map visualization person necessarily, but so I'm going to translate this to a different context and then sort of try to back out how it applies to maps. So another context that's very similar in a certain way is communicating uncertainty in something like a heat map. So here I have a data set on the left-hand side. You'll notice, so it's got 8 variables in it, and this is just a Scatterplot matrix. So each element here is one variable plotted against another variable. So y1 versus y2, for example. And you'll notice some of them are you know, highly positively correlated or highly negatively correlated. Some don't really have much correlation. You know, a classic way of representing this would be a correlation heat map, right? So when the correlation is high and positive, we've got a more blue color. When the correlation is high and negative, we've got a sort of more red color. And then kind of in between is sort of this muddier thing in the middle. But there's no uncertainty in the representation on the right-hand side. And so a question you might ask is, like, how would I inject uncertainty into this representation in a way that, you know, is useful? And if you imagine this were more like a map, like you can imagine these different cells being regions on a map, for example. Now, to make this a little bit easier to talk about, I'm just going to zoom in on the top 3 and start there, and then try to back out a reasonable representation. So here we have the Scatterplot matrix of these 3 variables. A really simple thing you could do. So in this case, I fit a multivariate regression model in BRMS. I have posterior distributions for the correlation in each of these cells. And then I've just plot those also as a sort of faceted plot. Now, there's a lot of problems with this plot. The first one right off the bat is that it's kind of weird to read. I'm not really taking advantage of any metaphor. And it is useful sometimes to talk about metaphor and visualization. And in this case, I think it is very applicable, which is I might think of high positive correlation as being up, and I might think of high negative correlation as being down. This also sort of mimics the orientation of the scatter plots. In this visualization on the right-hand side, I haven't taken advantage of any of that. And so, sort of to the left in this cell is negative correlation. To the right in this cell is positive correlation. If I just flip those cells, now I'm much more, I would argue, sort of taking advantage of the metaphor in order to communicate what's going on here. The other thing that I've done, and I'm going to talk about how you can do this in Ggdist in a little bit, is I've actually mapped the Y value of each slice from this density plot onto that same color scale I was talking about before. Blue, positive correlation, red, negative correlation. And the thing is, when you do something like that, so if I zoom out to the full chart here, you get something that's called a micro-macro reading. So basically, there are two kind of useful ways of reading this chart, at least. So one of them is the macro reading, which is I can kind of step back and squint, and I can still see, these cells up here that have negative correlation, these cells down here that have negative correlation, these two that have positive correlation. And the reason is that I can sort of just like the average color in each cell, or the average color of these densities, which is actually going to correspond to the average of that posterior distribution in that cell. But I also have the micro reading. I can go in and I can look at an individual cell and look at the distribution itself, and think about, like, what's the variance of this distribution? Where does it lie relative to 0, and so on. And actually, I've overlaid a white line at 0 to try to make that a little bit easier. So this is something called a micro-macro reading that you often get in these complex visualizations where you have sort of multiple things you're trying to communicate simultaneously, or in this case, the faceted visualizations are what are sometimes called small multiples, because there are small versions of the same chart multiple times. But I wanted to also try something a little bit weirder to sort of talk through some of the other implications of kind of weird uncertainty visualizations you can come up with. So what I'm going to do instead is, in every cell in this chart, I'm going to take, for every pixel in that cell, I'm going to take a draw from the distribution in that cell, and I'm going to color that pixel according to that draw. And then I get something like this. And here, I'm kind of moving more towards that discrete representation again. And I'm also taking advantage of this sort of ensemble processing thing that we can do even a little bit more explicitly. So ensemble processing, back in the day when we didn't have monitors and image formats that supported millions and millions of millions of colors, right? We would have, say, this, which is like an 8-bit image with like 256 different colors in it, trying to show more than 256 sort of effective colors. And the way that it does that is it uses a palette, sometimes with some pretty weird colors, that when you look at it from far away, your eye will average over that and create a sort of a palette with more colors than actually exist here. But when you zoom in, you see some of these like pretty strange things, and you will notice that it's really actually only a much smaller set of colors in this image. And the same sort of things going on here, right? So I can see the average color of these different cells. I can also, in a way, I can judge the uncertainty a little bit, because I can see, a little bit of how much red or how much blue is in there, but also how grainy each cell is tells me a little bit about the uncertainty. In the map context, so here's an example in the map context. You can see it a little bit better, I think. So here are two counties with relatively similar average color. And this is a map of poverty rates and the uncertainty in that. Well, this county happens to have a city in it, probably has a higher population and therefore less uncertainty in if there's a higher sample there, there's probably less uncertainty in the poverty rate as a result. So it makes sense that this is a more uniform color than this one. Now, I talked earlier about deterministic construal errors in the hurricane context, and this is where uncertainty visualization gets really tricky. So I would argue that in the correlation heat map situation, this kind of pixelization approach or dither approach, it's hard to imagine misinterpretations that people might have there. There's an obvious misinterpretation that exists in the map context that wouldn't exist in the correlation heat map context. And that is that, again, location means something on a map, right? So I could see a reasonable misinterpretation of this is that people would make this kind of deterministic construal error, thinking that the dithering is actually trying to communicate like really fine-grained measurements of poverty rate, which, if you think about it, don't really make sense, but it's a reasonable misinterpretation because location on a map typically corresponds to location in the real world. So it's like the exact same uncertainty visualization. You pick it up, you move it from one domain to another, and all of a sudden there are ways that it could be misinterpreted. And this makes it really hard to reason about uncertainty visualization effectiveness. And really the point that I'm trying to make through a lot of these examples is that building effective, complex, and correct uncertainty visualizations is hard. Like it is just, there's a lot of things to consider in terms of the task, in terms of visualization perception, in terms of uncertainty cognition, and the domain itself, that I struggle to say like one size fits all, like this is a good uncertainty visualization for this type of data always, right? Like it's just that kind of recommendation just doesn't exist. And as a result, if you're trying to build uncertainty visualizations, you need to be able to prototype quickly. You need to be able to try a bunch of different things and sort of navigate this, what in the HCI sense we usually call a design space, which you can think of as this like huge multi-dimensional space of all of the visualizations you could potentially create for this problem. And if you start in one part of the design space and just sort of hill climb a little bit, you're probably not going to find a great solution. And so it's really hard. And, this motivates a lot of the stuff that I've been doing in terms of tool building, like munging posterior draws into the exact shape that you need for a particular visualization is often just an incredible pain. And so that is where things like tidybayes and ggdist have started to come in. And before I start talking about that stuff, I think this is probably a good spot to pause.
Right. While we're pausing, so a couple of questions came in. Mm-hmm. Can you hear me well, Matt? Yeah.
Perfect.
Right. So from your experience, which uncertainty visualizations work best for people that are not aware of the importance of the uncertainty? Well, namely people that are not educated or savvy in statistics. So that's like something related to experience and technical savviness, or maybe you have some other matrix how to judge people's ability to process uncertainty.
Yeah, that's a really good question. So I think I have a couple of thoughts about that. So one is in the bus catching scenario, for example, we recruited a chunk of people who are like just normal transit users in Seattle for one of our surveys, and found that they were able to make better estimates with like the quantile dot plots, for example. Now that doesn't always translate. We've done some other experiments where that style of representation turned out not to be the most effective for the particular task at hand. But that I think the discrete representations of frequency framing representations often work pretty well. one of the things that we have found, so we've done things like we've included numeracy scales in some studies, and generally speaking, I think that people who are more statistically literate do better with like every uncertainty visualization type that you have, right? And so it's almost not a question of like, is there a representation that happens to be better for people who aren't stat savvy? There are representations that tend to be better for most people, but you know, there isn't like a, well, we haven't studied it, and it would probably take a pile of people to do it, but we haven't looked at anything like any sorts of like interaction effects of like things that happen to be better for stat savvy people and not for other people. I think you would need a really large sample to even like try to tease out an effect like that. There was something else I wanted to say about that. Not aware of it. Yeah, so one of the other things that sort of comes in is that like sometimes what you want in an uncertainty visualization is just to like convince people that there's uncertainty there. And maybe they aren't even really doing a particular task with that uncertainty, right? And this is where I think sometimes you get people using things like, you know, blur or like gradient plots and stuff like that, which are not particularly accurate representations. It's really hard to correctly retrieve information or integrate over information from a gradient plot. But it is often, I think, more obvious to people that is trying to communicate something about uncertainty. And so this is one of those trade-offs. And when you're thinking about tasks, like you can give up some correctness or like resolution if you just want to gain a little bit of maybe intuitive understanding where precision doesn't matter that much. But I mean, this is one of those things with visualization. Like you get some people with visualization who are like, no, like the only thing you can ever do is make the most accurate representation of the data, and like metaphor is irrelevant. And I think that that's a very poor understanding of how people interpret visualizations.
Brilliant. Yeah, thanks for that. Another question that came in from Jonathan, he asks, so we love the detailed representation of the uncertainty. Is there a way to put the pixelation into the legend in Ggplot too?
That's a really interesting question. That would be really cool. Like I could imagine having almost like the bivariate version of the legend or something like that, that was trying to show you how much of the dither corresponds to how much variance or something like that. Off the top of my head, like if I was going to try to do that, what I would probably do is actually just construct a separate visualization that is that legend, and then combine it with the other chart using like Patchwork or Cowplot or one of those packages that allows you to combine two different charts into the same view. I don't, off the top of my head, know that there's like a guide function for that kind of thing. I imagine there's not.
Thank you.
Yeah, that's a really interesting question.
Yeah, those are all the questions right now. Again, I want to encourage people to type in your questions. Either, well, chat is fine, but there's a Q&A. Thank you. Oh, okay, one more question just came in. Fabian asked, the quantile plot seems to be very close to Wilkinson plot, 1999.
Yeah.
Can you explain the difference?
Yeah, so it is actually using a Wilkinson dot plot. So the difference is the Quantile dot plot is taking quantiles and then displaying them as a Wilkinson dot plot. The Wilkinson dot plot, that paper, the 1999 paper, is really about using it to visualize sample data. So you aren't doing any summarization of the distribution before you plot it. In the quantile, so basically like the name just comes from, yeah, we're taking quantiles and then we're displaying them as a dot plot. So like imagine you have like a posterior predictive distribution with like, 10,000 samples in it or whatever. Then you take 20 or 50 quantiles from that distribution and then you display them as a dot plot. And that's how you would construct a quantile dot plot. So the real difference is like, I wouldn't use a quantile dot plot for displaying like raw data, for example. I don't think that really makes sense. You show the raw data as a dot plot. But if you have something like a posterior distribution or a posterior predictive distribution, showing the like 10,000 samples from that distribution is probably less useful for the purposes of people making decisions than showing them, say, 100 or 50, where, you know, the resolution of their the resolution that they can make, the reasonable resolution in the tails of the distribution that they can make is, you know, going to be covered by that. And it's going to be easier for them to actually see where the intervals they care about are, because the denominator is lower. If you show them like 10,000, basically you're not actually taking advantage of the discretized representation, because no one's going to be able to count enough dots for that to be meaningful. What they're going to do is they're just going to essentially reduce down to doing area estimation anyway. It's going to look enough like a density plot. You're just going to be like, well, what proportion of these things is to the left or right of a line, if that makes sense.
Thank you. That's it for now. Thank you.
Cool. Yeah, these are great questions. Right. So yeah, so prototyping these things is really annoying. Hence, you know, I started building tidybayes to try to essentially take posteriors from, well, originally I was using JAGs and then started using Stan and BRMS and RStanArm and stuff like that more these days. The idea is functions to try to take posterior distributions from these MCMC models and munge them into some form that is useful for plotting with Ggplot, because Ggplot really expects data frames, and in particular works best with like long format data frames. And so the idea behind long format being where, you know, you have only sort of variables in columns, and then each row is, say, one draw from distribution. So I'm going to do a couple of examples with tidybayes to sort of walk through some of the general ideas of its design that are intended to make it easy to create a variety of charts without having to completely reconfigure the code that you're writing. And that's really where I think like there's, when you talk about visualization design in terms of like API design, you know, sometimes it's like you want to build a function that just makes a certain chart type, and you're always using that chart type over and over again, and you just want that function, and you don't really need to customize it. If you're not making you know, a plot for communicating uncertainty to a broader audience, or you're not making a plot for publication or something like that, I think it's often easiest, and this especially comes up to me with like diagnostic plots. It's like, if I want a posterior predictive check where I'm just showing like a bunch of the densities and then the distribution of the observed data against those, yeah, like all I want is a function that can generate that chart. I'm not going to customize it much. So I don't need like a sort of bigger language for constructing custom charts. I think there's this other set of things that you want to be able to do where you are constructing custom charts and you are trying to navigate this design space of uncertainty visualizations and try out a bunch of things, where it's effective to have sort of modular pieces that you can put together. And so this pattern that I'm going to show you, this grid condition plot pattern, is a pattern that I've sort of developed over the years with tidybayes that's intended to allow you to easily construct custom charts. And so I'm just going to give a really simple example, and then when I do demos later, I might show some more complex things with this pattern. So here is a linear regression, 2 variables, X and Y, just fit a linear model to it using BRMS. And what I want to do is I want to construct this chart that's showing the data and a fit line and the posterior distribution. So these two credible bands around this posterior distribution for the mean conditional on X. And so I've got 95% and a 66%, uncertainty band here. But I want to construct it in a way where if I want to make other visualizations, it's going to be easy. So what I'm first going to do is the grid step. And the grid step is just, I want to construct a data frame that is a grid over my predictors. I can do that using the expand function from the tidyr package. You can also do it using the expand grid function from the model R package, or even if you want to, you could use like expand.grid from Bayes R. So there's a lot of ways to construct this. In this case, the data frame is not all that exciting because there's only one predictor, but you can imagine like if I had two groups, I might include or some other predictors, but say I had a predictor that was a factor with two levels, I could include that in this expand call and I would get two columns, like one for my continuous variable and one for my categorical variable, where that column is going to be repeated, or those rows are going to be repeated for the two levels of the categorical variable. So it's just doing all of the combinations here and then producing a long format data frame of those combinations. And this is, exactly the kind of data frame that you could stick into a prediction function from BRMS or from RStanArm. So, functions like posterior predict and posterior epred and posterior linpred, which give you the posterior predictive distribution or the distribution for the expected value of the posterior predictive distribution, which is posterior epred. So essentially the distribution of the conditional mean, or the distribution of the linear predictor, which is not that interesting in this case because the distribution of the linear predictor and the distribution of the conditional mean are the same, but in a lot of models, those are different. But instead of passing this into one of those posterior predictor, posterior epred functions, what I'm going to do is I'm going to pass it into a function in tidybayes that calls down to those functions and then reshapes the data into a format that's going to be useful for visualization. So in this case, it's a function called addEpredDraws. And essentially what this does is for every one of these rows in the input prediction grid, it's going to expand it out to, I don't know, say this model has 10,000 draws in the posterior. It's going to expand it out to 10,000 rows where each row is one draw from the posterior distribution. And it's going to give me these draws from, in this case, because I asked for epred, it's going to give me draws from the mean conditional on this X value, which is eventually what I want to plot, right? Now, you might ask the question, like, why would I go through all of this trouble of creating this giant data frame when really all I want are the intervals here? And as I'll show you in a minute, I think this is a valuable intermediate data structure because as an intermediate data structure, you can use it to generate a bunch of other charts. If at this point, if I went directly from this prediction grid to just the intervals, then if I wanted to do something else like a spaghetti plot, I'd have to like go back and adjust my pipeline more deeply. And so this is why I think this is a useful intermediate format. And a lot of tidybayes functions are geared towards getting to something like this as a step towards creating a visualization. That way, you're always sort of working in the same mode in terms of data structures, and you don't have to keep reshaping your data as much. Now, there's a family of functions in tidybayes called the point interval functions. And they're all named with a method of constructing a point summary of a distribution and then an interval type. Is median QI. So, there are other ones like mode _ HDI if you want mode and a high density interval, or you can do like mean QI or various other combinations of those sorts of things. And what these do is they actually take these long format data frames, which are constructed as grouped data frames. So this would be one group, this would be one group, and so on. And they summarize them down to whatever point summary and intervals you ask for each of these groups. So here, for example, this first group, say it's 10,000 draws from the expected value of the posterior predictive, conditional on x being 1, so way over here. This is going to give me the median and then the lower and upper limits of the 95% interval at that point. Now, the other thing about tidybayes is this sort of long format data frame kind of philosophy means if we want multiple intervals here, we want to do the 66 and the 95, we can just pass in the width parameter with multiple values in it. And you can give it an arbitrary number, although at a certain point, like it becomes a little ridiculous. So like 2 or 3 intervals is usually what you want. So here I could do dot width equals the 66% and 95%. And now I'm going to get, for every original row in this giant data frame, I'm going to get 2 rows, one with the 66% and one with the 95% interval. And now this is all that I need in order to construct the visualization on the left-hand side. So over here, I can chuck this into ggplot. I can, map this x value onto the x aesthetic, the x position on the axis there. I can map the expected value of the posterior predictive onto the y axis. And I can map the lower and upper ends of the intervals onto y min and y max, which are what are used by geom line ribbon to construct the limits of these bands. Geom line ribbon is a geometry. It was originally in tidybayes. It's now in Ggdisk because about a year or two ago, I split them into 2 and put all the geometries into the Ggdisk package. Geom line ribbon also, unless you set it otherwise, if your input data has a width column, will implicitly map that width column onto the fill color aesthetic in order to construct something that looks like this, right? So I'm basically mapping 66% onto the higher end of the color spectrum and the 95% onto the lighter end. And that's how I get these 2 different bands, one with one color and one with another. Now, the thing about this is I want this to be fairly generic though. And one of the parts of this pipeline that's a little bit annoying is the summarization step over on the right-hand side. So what I really want to do is make it so that I can directly put this long format data frame into ggplot and into ggdist. And so all of the geometries in ggdist that start with geom have a corresponding version that starts with the word stat instead, which can take these unsummarized data frames and do the summarization step for you. So if I just change this to stat line ribbon, I can pass in this full data frame to ggplot and get the output that I want. Stat line ribbon also takes a point interval argument, so you can change the type of point interval, point summary and interval if you want. And it also takes the width argument, so I can, in this example, I'm doing 50, 80, and 95% intervals now. And so now I have a sort of setup where if I want to start playing around, I can do that. I can shift to other sorts of visualizations I might want here. Before I do that, I'm going to show you what this code actually looks like. So this is the entirety of the code that's necessary to generate this plot. So the model is M, DF is the original data frame, the raw data. There's like 2 other little bits here at the end, which are just this line, geom point, is going to add the points on for the raw data. And scale fill brewer is just giving us that nice blue color scale instead of the default sort of ugly ggplot color scale. So that's all of the code that you need to generate this plot. And then the point of this, though, is this sets us up for more exploration of the visualization design space. And once you learn kind of this language, I think you can sort of put the pieces together to create even crazier things. I've seen people make stuff with like ggdist that I did not think about, which is really, to me, like that's like the best thing. Like seeing someone do something with this that is not something that I had considered is, to me, an indication of the flexibility of it. So one of the things you might want instead would be, say, like a posterior predictive distribution. And so if you want that, you want draws from Y conditional on X, you can use add predicted draws, which will call down to the posterior predict function from BRMS. And it gives you everything in essentially the same format. You now have this prediction column instead of the ePred column. But otherwise, you're doing the same thing. You're still using stat line ribbon, and really not much else of the pipeline changes. Or, I was talking about spaghetti plots before, right? So if I go back to the version where I'm just doing the expected value of the posterior predictive, then instead of summarizing these with something like stat line ribbon, I could just use a line geometry and group the values by the draw column. And that will give me one line for every draw from the posterior distribution for the mean. And in this case, I don't want to show 10,000 of those because it's going to be illegible. So what I'll do is I'll reduce the number of draws that are shown down to something reasonable like 100. And now I can get a spaghetti plot. And the reason that I think this data structure is useful is it's harder to see in the linear case, or it's harder to see the value in the linear case. But as soon as you have a nonlinear function there, this will allow you to draw sort of arbitrary curves from that posterior if you want to see what those look like. Okay, so my contention here is that like this pattern allows you to sort of put the pieces together in a modular fashion to come up with a visualization and to explore visualization design space more effectively. I don't know if there are any questions at this time, or if I should just keep going, because I can start talking about ggdist.
Not at this time.
Cool. So the other thing that I wanted to talk about was ggdist and sort of the idea behind it. And this really gets, in some ways, it's almost it's more interesting from a sort of abstract perspective, at least to me, sort of studying visualization, which is there a pattern that you can use to construct a large variety of different uncertainty visualization types? And in particular, can you do this in the grammar of graphics in something like ggplot? But the grammar of graphics really is this bigger thing. It's a formalism for describing visualizations. You don't necessarily need to use ggplot to use the grammar of graphics. And so the idea behind ggdist, or like the motivation behind it, is that if you derive a distribution describing your uncertainty, a posterior distribution, a posterior predictive or something, and then you want to visualize your uncertainty in some way, the idea is to just map properties of that distribution, say its location, its scale, its quantity, quantiles, its density, or its cumulative distribution function onto visual channels. In visualization parlance, we talk about visual channels often. In ggplot, these are usually called aesthetics. It's just like properties of things that we draw that we can map data onto, right? So like location, size, color, or even particular aspects of color, like lightness or hue or what have you. We usually call these visual channels. Ggplot sort of calls them aesthetics or scales. But the idea is to try to abstract the visualization construction process to this idea of deriving a distribution and then mapping its properties onto visual channels. That might be a little abstract, so I'm going to try to make it a bit more concrete. So these are from so this was back in May of 2019 or April 2019. So given a model of US unemployment and a prediction for what US unemployment values will be in May of 2019, what are some different ways you could communicate that distribution or that prediction? And if we're thinking abstractly, like what are the things that we are mapping onto visual channels? So here, for example, we could imagine there's a density plot for the unemployment, or there's a density function for the unemployment in May of 2019. It's being mapped onto the Y position. And that's the essence of a density plot. Obviously, there's a bit more to how you construct it, but if we're trying to boil it down to its essence, that's sort of what it is. A violin plot, by contrast, would be mapping that density function not onto just position, but onto, say, thickness or width or something like that. And this does actually make a difference, because the way that people perceive height against a common baseline is different from the way that we perceive width. And we're actually generally better at estimating height than we are at estimating width. And so it does matter that these are different. And part of the point of this exercise is you can then think about, well, what data am I mapping onto what channels, and what are the effectiveness of those channels? How well can people perceive those things? And therefore, how good is the visualization going to be at different tasks? And so we could map this density function onto, say, opacity to get a gradient plot. And it's that same question. And I mean, the interesting thing about this is we're not as good at retrieving lightness values as we are at retrieving width or height values. And so we should expect in general that gradient plots will not perform as well at tasks where that matters. And this sort of gets back to the answer I was saying before, like maybe that matters, maybe it doesn't. It depends on the situation. There isn't a sort of universal gradient plots are always going to be worse kind of recommendation that one could make. Or you could use, say, the CDF or the complementary CDF in order to get these sort of weird bar chart type things. I think these are sort of interesting. You can do this with opacity as well. And I think I have an example in a second where you can almost imagine building what I think of as like a generative story for an uncertainty visualization, right? Imagine you were constructing a bar chart for this one value, and you took a large number of draws from the distribution for what that bar chart could be, and you stack them all on top of each other and then squish them down. That's essentially what if you did that, you would get this complementary CDF chart on the bottom if you were doing it with horizontal bars. And so this is kind of the abstract view. If you translate this into what Ggdist does, it has these slab interval geometries, which are the core geometry to a lot of the visualizations in Ggdist. And there's a whole family that you can construct by essentially just tweaking the parameters of this slab interval geometry. So everything I'm going to show you right here, you could use these shortcut geometries, which I'm going to show on the left-hand side, but you could also construct them by just changing a couple of options to the slab interval geometry. And the reason why I think that's powerful is, yeah, I've constructed some shortcut geometries and put them as functions into Ggdist, but they're really sort of just the starting point for being able to explore an entire range of possible uncertainty visualizations that you can create. So the half-eye plot, for example, the name sort of comes from eye plots, which is what you get when you do sort of the violin with the interval in the middle. There was a paper that called them that like, maybe 20 years ago. And so that's where the name comes from. But this is really just, mapping the density function onto the thickness of this slab. So the slab interval geometries are composite geometries that consist of a slab and a point and an interval. And the eye plot is basically the same. It's just there's a parameter that determines whether the slab is drawn on the top or the bottom or on both sides. And if you change that parameter, you get the I-plot. Or alternatively, if you want a gradient plot, you just map the density onto the alpha channel, and you get a gradient plot, right? Or if you want a histogram, you can actually change the function that's used to calculate essentially the density, and then you get a histogram version. Or if you want a CDF, you can change it to the CDF. And so this is, again, these are like some of the basic shortcut geometries that you can use, but there's like a bunch of crazy things that you can do with it, right? So you could, instead of mapping the CDF onto the thickness, you could map it onto the alpha value and then get this kind of like fuzzy bar chart, right? And you can imagine like a bar chart with a bunch of these. As the uncertainty is greater, you get fuzzier bars. If the uncertainty is quite low, you get a very precise bar that would look even closer to sort of a standard bar chart. Maybe you're doing something where you have a region of practical equivalence that you care about, or like some other region of the distribution that is, important to your domain. You can map, some binning of the X values onto the fill aesthetic, and then get the density sort of filled in the region that you care about. So here it's just everything between plus or minus 1.5 is going to be filled in a different color. There are some other crazier things that people proposed in the visualization literature, like, fading out the tails of the distribution outside of, say, the 95% interval. So this is like one way of doing that. Or, if you have particular intervals that you want to highlight in the density, you can do that. This cut CDFQI function is just a way of discretizing the CDF based on some desired interval sizes, which if you map onto the fill aesthetic, then gives you kind of this sort of appearance to the density. And again, these are just like a couple of crazy ideas that you can sort of start with. And even like so this, which I showed before, is really just a half-eye geometry with the Y position also mapped onto the fill color. That's like the core of what makes this chart. And so, in developing it, in sort of doing the design process, like exploration of this thing, the distance between, putting a half-eye chart there and then deciding that I want to try to fill the fill color according to the Y position is basically just like one line of code. And so that really reduces the friction when you're sort of doing this design exploration, which I think is really important. The other thing I just wanted to point out here is you can now, if you have R 4.1 and you're using like the Cairo graphics engine or PDF output or SVG output, you can use fill type equals gradient as a parameter to any of the slab interval geometries now. And it will use the new like linear gradient support in R 4.1 to make nicer looking gradients. You can generate this chart without it, but sometimes the gradient will look kind of weirdly choppy because it's actually being generated as a whole bunch of tiny segments. With R 4.1, we actually have true gradient support in the graphics engine now, which is awesome. And Ggdisk supports this. Okay, so the argument that I want to try to make and why you would want to use something like this is that it allows you to quickly prototype a whole bunch of designs without learning a bunch of like little chart type functions. They are like, you can use the shortcut geometries, but they are all just the same geometry with different options applied. And you can try to reason about visualization effectiveness by thinking through what data is being mapped onto where, what parts of the distribution can you see, and through what visual channels. And then, how good are those channels at communicating information? So for example, So this is that same unemployment model that I was talking about before. So I just fit a really stupid model to this data for demonstration purposes. So it's a Bayesian structural time series model from the BSTS package. And I really just did it in order to demonstrate sort of some of the different ways that you can play around with uncertainty visualization. And you can see a link to it down at the bottom there. So here, this is just showing the raw data. Unemployment as measured by the Bureau of Labor Statistics in the US. And then according to the model, the uncertainty in that measurement in April of 2019. There's a bunch of other ways that you could sort of try to communicate this, right? So you could do a bunch of density plots. So this would be like stat slab in ggdist. Here we're also showing like the uncertainty in the predictions versus the uncertainty in the measured values. Now there's a couple of things that are different. So if I look here, we've got like monthly measurements, and here we're actually only showing every 6 months, I think, yeah. Because you lose time resolution when you're doing something with a bunch of density charts like this. And so there's this trade-off. It's like, well, you know, position is a good encoding, so it might be helpful for the density plots to be encoded that way, for the uncertainty to be encoded that way, but I do lose time resolution. So if I care about that, then I might want something else. An obvious contrast would be something like a gradient chart, because here I gain back the time resolution, but it is really a lot harder to see the extent of these distributions when they're encoded this way. And so I'm losing sort of uncertainty resolution by doing this with a gradient instead of by doing it with something like a density plot. So as a final sort of weirder option, this is the so-called like complementary CDF bar chart. So I imagine this could have been a bar chart, and now I'm kind of like stretching the bars in proportion to the uncertainty or something like that. One of the values here is, again, if the thing that I care about is like how large could unemployment be at a particular time point, or what's the likelihood of unemployment being above some threshold, this is going to help me with that, because I can kind of make some estimate of how far along this is proportionally on the x-axis here within one of these bars, and then be like, well, you know, there's like a 95% chance it's going to be above this point or something like that. So again, it kind of comes back to tasks and like trade-offs and the different things you want people to be able to get out of a visualization. So to me, a lot of reasoning about effectiveness means like thinking about accuracy of visual channels, also thinking about you know, trade-offs in resolution of other variables. Like uncertainty is often this thing that you're trying to put on top of some other variables that you also care about. And so you are often losing something else in order to add resolution to the uncertainty. And so there is no like one perfect solution to a given design. And then you also have to think about what tasks your audience is doing, and what metaphors you might be able to employ to communicate more effectively to them, depending on what sort of audience you have. And this is where things like maybe a gradient plot might be useful, or something else. Okay, I think now is another good point to pause for questions.
Yeah, Ulrika had a question. Do you want to answer it yourself?
Yeah, I can do that. Yeah, so if you go back to the slide where you show the time series of the employment, the previous one, I was where you show the red things to the right.
Oh, yeah.
Yeah, so this is often showing that we are very uncertain about the future unemployment rates. But I was thinking that have you done this graph, but you have sort of backed the tape and you have tried to describe their uncertainty at the time when they made the predictions. So for example, back in 2017, they only had 3 one data point. So maybe uncertainty was very large at that point. And then it maybe became less when they got more data, but then when they got this hump, it sort of grown and then it reduces again. So that would sort of give another idea of that we are not that uncertain because we have a long time series.
Yeah, I think there's some really interesting questions here. I mean, I've seen charts like that, and I had one not for this, but for predicting vaccination rates in the US, where it was showing sort of animations over time of previous predictions and their relationship to the data, what actually happened, which is, I think, is a pretty common like time series uncertainty thing that you see. To me, I think there's a really interesting question, and I have a postdoc joining me in the beginning of next year, where we want to try to tackle something in this vein related to election forecasting, which I think is really kind of what you're getting at, which is like, you know, if you're seeing forecasts for what's going to happen on election day over time, and you're seeing the uncertainty in those forecasts, and you're seeing, you know, the forecast and its uncertainty change over time as, say, like a consumer, like an audience member of the public, right? Like how do you actually integrate that into your understanding of what you think is going to happen, right? How does that impact your trust of the forecaster themselves? I think I don't know good answers to that question. I'm optimistic that, you know, so like the Plinko example that I gave, or something in that vein, where we're really trying to communicate that there is uncertainty in this process in a way that is, you know, somehow more related to things that people already associate with uncertainty, might help them like understand that there isn't just like, we're not just saying like, this is exactly what's going to happen and you should, you know, believe it and trust it, or like take the point estimate or whatever. I saw another really interesting example, the Canadian federal election. Let's see if I can find it. I think it's this one right now. The Canadian Broadcasting Company has this as their one of the things in their forecast visualization thing, which is, you know, some kind of like ball machine that like spits out balls in proportion to their forecast distribution for the two major parties, right? Like, I think there's some interesting potential in this vein of like seeing these things, right? I mean, and like seeing how they impact people's understanding over time, right? Like, this is one snapshot in time, but this thing has been running since the beginning of election polling in the election. I don't know how people respond to it if they see it over time and how it impacts their understanding of what's going to happen.
So there is Fabian, he's asking where to find the slides to this amazing talk.
Oh, thanks. I'll post them on my website.
Yeah.
And then we can send out a URL later, I guess.
Yeah. I have also another question. I've been lumping them up here. So I was just thinking about the distinction between data visualization and uncertainty visualization. And if I understand it correctly, uncertainty visualization, at least what you're doing, always starts that you have a probability distribution that you would like to visualize. Whereas data, you can have all sorts of things, and you want to visualize data itself or the results from doing some kind of analysis on data. Mm-hmm. Could you elaborate a bit on that?
So that's an interesting question. Yeah, so one of the things that has been interesting, I think, especially about Ggdist, is running into a little bit of this distinction. Is I had originally designed it for uncertainty visualization, and not with the intent of visualizing like sample data, for example. Even though, I mean, like, you can think about it as that also as being distributions. And of course, you can visualize them often using the same idioms. And I think that that's, it's a really hard point, because once you start visualizing those things to an audience, that so there's this notion of like visualization schemas in sort of some cognitive scientists that study visualization talk about this. One of them, Lace Padilla, talks about this, for example. She also studies uncertainty visualization, but she has like a cognitive science background. And she has a really interesting paper on this. And one of the problems that you can run into in visualization is it's not just the visual encodings, right? It's the schemas or like templates that people have for charts that they've seen before and how they expect them to work. So a really good example to me is if you have a paper where you're showing, let's see if I can find an example. So if I show someone a chart like this in a paper, there is a very reasonable chance that they will misinterpret this as density plots of the sample data, of the raw data, and not as posterior distributions for the mean, right? And that's simply because like often you see charts like this and that's what they mean, right? So that impacts some things, right? So like one of the differences, I think, between sort of the default way that these visualizations work in Ggdist, in the way they look, and what you might imagine is like the obvious counterpart, which would be like a violin plot, like a more traditional looking box plot, with then like the violin around it, is it's a bit of an intentional design choice to make them look more like inferential intervals that we tend to associate with inferential quantities than raw data. I don't know how well it works. I think that really, like, honestly, in a chart like this, you need a giant label that says this is not raw data. Don't think about it that way, because otherwise you're going to run into this problem. I don't know if that answered your question, but that was what I thought about when you asked that.
Thank you. Yeah, no, it was very good.
Yeah.
I think we should continue.
Okay.
Unless Dimitri or Rasmus have spotted any other questions?
No questions at this time.
Okay.
I think so. For people that are wondering how long we can go, I think we have another, maybe at least I'm counting that we will be definitely done in 20 minutes. But if you have any more questions, please feel free to shoot them into the Q&A or chat, and Matt will answer them before we close.
Cool. Yeah. So at this point, we've reached the end of the like structured slides that I wanted to have. So I'm going to try to do a couple of little demos. I basically just have a list of things that I thought it might be interesting to talk about. And so as I'm doing this, please interrupt me if questions come in, because I'm happy to shift to other things, or people have questions about whatever I'm demoing. One of the things that I actually wanted to, given that I only have 20 minutes left, let's see, what is a good thing to demo? So one of the things I did want to mention, and I hope that the font size is decent here, is good enough, but one of the things that I wanted to mention, so I alluded to the posterior package kind of near the beginning of the talk. This is another package that I've been working on with Paul Christian Berkner and Jonah Gabry, and it's intended to do a lot of things, but one of them is also like helping munging posteriors in sort of a variety of formats. So if you have them as like matrices or lists of arrays or data frames or what have you, it's intended to help you convert them between those various formats. So the way that I think about it is like posterior is sort of even earlier in the pipeline than something like tidybayes. And so the way that I've been using it is it's really useful for some munging early in the pipeline. It also has a lot of modern diagnostics that have been put in there from the Stan group. Things like new variants of like effective sample size and things like that that are really helpful. And then tidybayes can now take the output of Posterior and easily transform it into the long format data frames for visualization. But one of the other cool things that I've been working on, especially in Posterior, is this random variable data type for R that is intended to look like a array or a matrix, but is actually a sample from a posterior distribution. So it's essentially like a random array or a matrix. So Posterior has, let's see, this example draws function just gives us a data structure with one example posterior in it. So this one is using the draws array format. And it's just got a couple of variables, mu and tau and theta. But if I convert this into the draws rvars format, which is essentially a list of random variables, what I'll see is these sort of slightly weird looking rvar things. And what these are telling me is this is a random variable with 100 draws and 100 iterations and 4 chains. And it's just a scalar value. So it just has, or it's a vector of size 1. Theta has actually been transformed into this random variable as a vector of size 8. And so it looks like a vector, but it's actually, if I look under the hood, which I can do with this draws of function, whoops, and I'll just look at the structure of it so that you can see what's actually going on here. Under the hood, it's actually an array where the first dimension is the draws. But the cool thing is, you know, I can treat it as an R vector insofar as that's possible. There's some corner cases where it doesn't work, right? But like, you know, I can do math on it. I can even visualize it with ggdist, for example. I can put it into a data frame, right? So I can say, well, I want a tibble where x is going to be 1 to 8 and theta is going to be this thing. And now I have a tibble or a data frame with this random variable column. And it's just telling me the mean and the standard deviation, but all of the draws are still in there. So I don't have to deal with this giant like 100,000 row data frame anymore. It's a little bit more manageable. I can kind of look at it and inspect it a little bit better. And then if I want to visualize it, I can actually do that with ggdist. So I can use the, I didn't demo this in the talk, but there's another set of geometries. There's the stat slab interval geometries, and then there's the stat dist slab interval geometries. And the stat dist ones can take rvars. They can also take distributional objects from the distributional package, which allows you to do analytical distributions. And maybe I'll demo that in a second. That's really useful if you want to visualize priors, for example. So here I can say, well, I'll map this X thing onto the X-axis. I will use theta as the distribution. So this dist aesthetic is a sort of fake aesthetic that you can pass distributions to. And then I can do like a half-eye geometry, for example, and I'll get all of these theta values. And so the idea is, you know, if doing these sort of long format data frames is kind of a pain, and it can be a little bit easier to sort of read what is actually happening in your data frame if you use this RVAR data type. You can even, there's another, let's see, example draws. There's another example in Posterior that's just like a Posterior for a multivariate normal. This, for example, has a covariance matrix in it, and you can see it's actually displayed as a matrix. So if you have like a posterior for a matrix or an array, it's a little bit easier, I think, to read in this RVAR format, where you can actually see the structure of that thing in the same way that you would for a variable, an array, a normal array in R. And you can do like, matrix multiplication and stuff with it too, if you want. There's some examples of that. Let's see. I'm not going to run through that example, but there are examples of that in the tidybayes documentation now. So there's a vignette on using tidybayes with Posterior. And there's some kind of, I think, neat examples, especially for ordinal models that show things like, so this is an ordinal regression just from the MT cars data set. So it's not interesting data. It's just trying to predict the number of cylinders in a car engine based on its miles per gallon, which, at least in that data set is not that difficult. But there are certain things that you can do. So like you might want to, from this ordinal model, construct a prediction for the average, like the expected number of cylinders in the car. You can do that essentially by just doing a matrix multiplication of the various cylinder levels by the posterior for the probability of different cylinder values. And in fact, you can express that directly as a matrix multiplication using this, which is actually a random variable, and this vector of cylinder levels. And then you can generate, say, this spaghetti plot pretty easily. I don't have enough time to really go into all the details of that example, but if you're interested in it, it's there. I think that this is kind of a cool direction for where a lot of the Ggdist and tidybayes stuff is going to go now that this RVAR data type is supported in Posterior. And if you're interested in that as well.
Matthew, could you zoom in a bit? It's a bit small.
Oh, sorry.
Yeah.
So we're basically just doing this matrix multiplication. This column here is a random variable matrix. So it's the columns are cylinders. The entries are posterior distribution for the probability of that cylinder conditional on miles per gallon. So that if you do this multiplication, you get the mean cylinder value, the distribution for the mean cylinder, which is this sort of spaghetti plot here. Yeah, I probably didn't explain that very well, but it's explained in this document if you're interested. The point that I'm trying to make is to try to sort of whet your appetite for why this might be a fun thing to play with. So if you're interested in that, there's this vignette, and there's also in Posterior, there's a couple of great vignettes. So one of them, the getting started vignette, just talks about the draws format and the couple of different formats that it has. And then the random variable vignette talks about like these random variable data types and the different operations you can do with them. And I haven't touched everything that is there, but you can do sort of most of the things that you would, I hope, want to be able to do in terms of just basic math with them. They try to mimic as much as possible base R arrays. Yeah, I mean, we've got 10 minutes left, so I think I'll pause there and see if there's anything else to talk about.
Okay. Yeah, let's see if there are any questions from the...
No, I don't think that we have any more questions here in the chat. Yeah, go ahead.
Yeah, so I think I'll wrap it up there. I think there's a number of other things that tidybayes and ggdist can do, but the big focus for me has been, if I can switch back to my slides, wherever I put them. The big focus for me has been thinking about this question of like how you develop a sort of language for specifying and reasoning about uncertainty visualization. Some of my research goes into this as well. There's a paper we published last year on something we call the probabilistic grammar of graphics, which is an attempt to more formally integrate probability distributions into something like the grammar of graphics. But I think the other thing, I think the thing that excites me about this, and I think one of the reasons why, so I sort of make an analogy to one of the reasons why I think people get excited about Bayesian statistics in the first place, which is the sort of frustration with the, like, you know, I need to learn how to specify and write like every single little different model type. And I'm going to need a different way of fitting every model and some like, you know, specialized functions for every single model that I could possibly imagine. And why not think in terms of some more general language for specifying statistical models that encompasses a large set of possible models you might imagine. And I think this is what is often a draw to things like JAGs or STAN or even BRMS, which itself is essentially a domain-specific language for a huge class of models. And the way that I have been thinking about things like ggdist and tidybayes is, what is a domain-specific language for all of the different sort of data transformations you might want to do to a posterior, or all of the different uncertainty visualizations you might want to construct, so that you aren't saying, oh, I need like to learn all the parameters for some new function in order to make this one chart, right? It's, I want to figure out how to combine the like atomic elements of this language in order to construct the chart that I need, and, you know, become fluent in that language in a way where you don't have to, you know, constantly be looking at documentation or something like that. That's my goal. I don't know if we'll get there, but that's, you know, the gradual evolution of these packages has been towards something like this. And that's it. Thank you for your time. This was a lot of fun.
Brilliant. Thank you. Very inspiring session, Mariana says. And then, so we are, you know, absolutely privileged to have you here. Thank you. So just to wrap up, thanks, Matt. And I just wanted to say that we're going to have more sessions in the near future, still under the Bayes Lund flag. The next talk, we're going to look at stun targets and targets in general for processing and basically lining up your Bayesian analysis into the pipeline. That's a very inspiring talk as well. And I think we'll have to come back to posterior. And if Matt or anybody else would like to volunteer, or maybe volunteer your colleagues to look closer into the posterior format, that's another technical topic that I really want to explore. Many good innovations are happening in that domain. And it's very inspiring to see these examples that you showed today. So I think we're about to wrap up right now. Thank you so much again for the talk. Thanks for everyone who turned up for this webinar. Looking forward to seeing you again. Stay safe.
Thank you so much.
Thanks.
I will stop recording just if someone is asking what's happening. Can you stay a bit, Matt?